You probably grew up picturing one ultimate telescope that collects all the secrets of the cosmos for us. Maybe in your mind it hangs in space, a single eye staring into the dark. It feels natural to believe there must be one champion that beats all the others. But when you look at what astronomers use, the picture gets much stranger. Some of our sharpest eyes ride inside jumbo jets. Others are not mirrors at all, but detectors buried under Antarctic ice, waiting for faint particles. Once you notice that, the question flips from which telescope is best to why we have to build bizarre ways of seeing and how far we can push them. At first glance, the problem seems simple. Our eyes are small biological cameras. They use a curved lens to focus light onto a layer of light-sensitive cells at the back of the eye. That light has to bounce off an object, pass through space, then squeeze through the narrow pupil and come to a sharp point. If the focus is off by even a tiny amount, the image on the retina turns soft. A telescope is like a giant artificial eye. The mirror or lens at the front plays the role of the cornea. The point where it focuses light is like the retina. Make the mirror bigger and the eye should simply get better and better. More light, more detail. Problem solved. Except that is not what happens when you actually try to see the universe as it really is. If all we had to do was scale up the human eye, astronomy would be easy. In reality, every time we fix one limit on our vision, another one appears. Start with the most obvious one. Human eyes only see a tiny sliver of the electromagnetic spectrum. We call it visible light, but that is only because it is visible to us. The universe does not care which wavelengths happen to trigger the chemistry in our retinas. Stars and planets and galaxies glow in radio waves, in microwaves, in infrared, ultraviolet, X-rays, and gamma rays. If you only look with visible light, you are like someone trying to understand an orchestra while wearing earplugs that only let through the flutes. So the first reason telescopes get weird is that they have to catch light we cannot see. A radio telescope is basically a giant metal ear that listens to the sky. An X-ray telescope cannot sit on the ground at all, because Earth's atmosphere blocks nearly all high-energy radiation. To see that sky, you either have to send delicate detectors into orbit, or in a few cases, hitch them to high-altitude balloons and rockets that briefly punch above the atmosphere. Infrared telescopes even have to be kept colder than space itself, or they will glow with their own heat and blind themselves. Each of these tricks is a workaround for the same basic problem. Our biology was never meant to be a universal camera, so our technology has to stretch and twist itself to fill in the missing senses. Then there is the atmosphere, the layer of air that makes Earth warm and breathable, and also constantly ruins our view. To a telescope, the stars shimmer and smear and dance as moving pockets of warm and cold air bend the path of starlight like water flowing over a stone. The bigger your mirror, the more of this chaos you collect. For decades, the solution was to escape it entirely. Put your telescope on a mountaintop in Chile or Hawaii, somewhere dry and thin and stable. Or avoid the problem completely and launch a telescope into orbit, far above the weather. That is how space-based observatories like the Hubble Space Telescope earned their reputation as the ultimate eyes on the universe. Up there, there is no weather, no city light pollution, no wind shaking the mirror. Hubble delivered crisp views of galaxies and nebulae that rewired how the public thought of the cosmos. It is easy to look at those iconic images and think the story ends there. We solved the atmosphere problem. We just need more Hubbles. But once again, reality is more awkward. Putting a telescope into space solves one set of limits and replaces them with another. You can no longer send a technician to tinker with mirrors and instruments every weekend. You are limited by rocket size, by vibration during launch, by the slow chewing of radiation and micrometeoroids. Servicing missions like the ones that repaired Hubble's flawed mirror are rare, expensive, and risky. For most space telescopes, once they are up, that is it. If something jams or runs out of coolant or fuel, the mission is over. So ground-based telescopes never went away. Instead, engineers got clever. One of the strangest and most powerful tricks they use now is called interferometry. Light is a wave. If you can collect the same wavefront at two different places and then bring those signals together with exquisite timing, the peaks and troughs will interfere. Spread many smaller telescopes out over a wide area, and in the right conditions, they can act like one giant virtual mirror with a diameter equal to the distance between them. This is how some observatories on Earth can now study features that are billions of times fainter than what your eyes can see, and reach sharpness that rivals or even beats orbiting telescopes. At the same time, another technology quietly attacked the atmosphere problem in a completely different way. Instead of running away from the turbulence in the air, adaptive optics fights it in real time. The idea sounds like science fiction. You fire a laser into the upper atmosphere to create an artificial star, a glowing dot of excited atoms. You watch how its light twinkles as it comes back down through the air. Then you use that information to flex a thin mirror hundreds or thousands of times every second, gently warping its surface to cancel out the distortion. Seen from the ground, the sky stops boiling and snaps into focus. A galaxy that was a smudge a moment ago becomes a sharp whirl of arms and dust lanes. A star near the center of the Milky Way turns from a fuzzy point into a trackable object whose tiny motions reveal the pull of an invisible black hole. Notice the pattern. Our best telescopes are no longer just bigger versions of a glass lens pointing at the sky. They are elaborate machines built around very specific obstacles. Some battle moving air, some battle thermal glow, some battle the fact that low-energy radio waves are unimaginably long, so their antennas have to be spread out over deserts or even over the whole planet. Others quietly endure the cold and darkness at the South Pole, where months of night and clear, dry air let them watch the faint afterglow of the Big Bang. From the outside, these observatories can seem almost whimsical. One looks like a fortress of white domes under the driest sky on Earth. Another looks like a flying warehouse with a door cut into its side so a telescope can stare out at the stratosphere. Another is not a telescope in the traditional sense at all, but a grid of sensors buried deep in ice that waits for ghostly particles called neutrinos to pass through. The theme is not elegance. It is brute compromise with reality. Each design is an argument between what astronomers would love to measure and what the universe and our planet will actually allow. If you follow that thread, you reach a deeper truth about why telescopes keep getting weirder. Every new machine we build starts with a simple scientific desire. Something like, we want to see the first galaxies, or we want to know what is really happening around the black hole at the center of our galaxy, or we want to be warned when a city-killing asteroid is heading our way. Then the constraints pile on. Light that has traveled for billions of years arrives stretched into longer wavelengths by the expansion of space. Faint signals are buried under the glow of Earth's atmosphere and the heat of the telescope itself. Moving parts flex and sag under their own weight. Budgets squeeze dreams into smaller rockets and cheaper materials. So when someone asks, what is the best telescope in the world? The honest answer is a counter-question. Best for what? The telescope that tracks a single star for 30 years to weigh a black hole is not the same machine that patrols the sky every few nights for dangerous asteroids. The one that listens to whispers of hydrogen gas from the early universe is not the one that photographs the dusty rings where new planets are being born. It is tempting to look for one instrument to rule them all, the way we look for a single flagship smartphone or one perfect camera. For every Hubble that fills posters and screensavers, there are observatories whose nicknames and acronyms rarely appear in the news, yet they quietly reshape our understanding of reality. A radio array that draws an image of the shadow around a black hole. A desert observatory whose careful measurements of carbon monoxide in distant galaxies reveal how fast the universe was forming stars billions of years ago. A forthcoming survey camera that will capture the entire sky in motion, letting us watch supernovae, colliding stars, and wandering asteroids as they unfold in real time. All of this rests on a simple but humbling fact. Our own eyes evolved to spot predators and fruit and the faces of other humans at walking distance. They are almost useless for seeing the universe as it truly is. So we build glass and metal extensions to our senses, and each generation of telescopes pushes against one more barrier. In the process, we keep discovering that the universe is stranger and more dynamic than the tidy diagrams in school textbooks ever suggested. In the minutes ahead, we are going to walk through some of the most powerful telescopes you have probably never heard of, and see how each one bends the rules of sight in a different way. We will stand inside a fortress of mirrors in the desert, look at a gold-segmented eye unfolding far beyond the moon, ride along with a flying observatory, and even dive under the ice at the bottom of the world. Along the way, we will keep asking the same quiet question. If this is what it takes just to see what is out there, what does that tell us about the universe we live in, and about the limits of our own ability to understand it at all? To get a sense of those limits, it helps to step inside one of the strangest eyes we have ever built on our own planet. High in the north of Chile, on a lonely mountain in the Atacama Desert, sits a cluster of white domes that look almost modest from far away. Up close, they are anything but modest. Each one houses a telescope the height of an office building, with a mirror so wide it could swallow a house. At night, the domes slide open, these giant eyes turn, and the quiet rock of the desert becomes one of the sharpest vantage points on the universe that humanity has. This is the Very Large Telescope, and the way it works tells you why the idea of a single best telescope is more myth than reality. The first surprise is the name. Very Large Telescope sounds like a joke someone forgot to change, but astronomers tend to be literal when it comes to hardware. What you see on Cerro Paranal is not one telescope, but a small city of them. There are 4 main giants called unit telescopes, each about 25 meters tall, holding an 8.2-meter primary mirror at its heart. Scattered among them are 4 smaller buildings that roll on rails. These are auxiliary telescopes with mirrors 1.8 meters across. They can be moved into different positions around the site, like chess pieces slowly sliding into formation before a match. Each unit telescope can work on its own as a fully independent observatory. Inside the mountain, a honeycomb of tunnels and rooms holds a rotating cast of instruments that can be fed with starlight from any of the big mirrors. Spectrographs split the light into its colors to read the chemical fingerprints of distant gas and stars. High-speed cameras freeze the flicker of planets passing in front of their stars. Infrared instruments peer through dust clouds that would be opaque in visible light. The Very Large Telescope has been steadily upgraded since it officially finished construction around the year 2000. New instruments arrive, old ones are retired, and the whole complex quietly evolves as science questions change. Viewed from above, though, there is another pattern hidden in the layout. The positions of the telescopes across the mountaintop are not random. They form long baselines, straight lines and triangles spanning tens to hundreds of meters. Those distances matter because of the trick that makes this observatory special. The 4 unit telescopes and the 4 auxiliary telescopes can be linked together as one virtual instrument. Instead of looking at the sky with a single mirror, they can combine signals from many mirrors spread out across the mountain, turning the entire summit into one giant synthetic eye. This trick is called interferometry, and it only works because light behaves like a wave. You can imagine dropping 2 stones into a pond and watching the ripples spread and overlap. Where the crests of the waves meet, the water rises higher. Where a crest meets a trough, they cancel out and the surface flattens. Starlight arriving at Earth carries a similar pattern of tiny peaks and troughs, except with wavelengths much smaller than the width of a human hair. If you collect that light at 2 different telescopes and bring it back together in just the right way, the waves will interfere. The interference pattern encodes information about the fine structure of the object that sent the light. In practice, this is desperately hard. The light beams from each telescope have to be guided through underground tunnels and into a central laboratory called a beam combination room. Along the way, movable mirrors ride on precision rails called delay lines. Their job is to adjust the path length of each beam so that all the peaks and troughs of the light waves arrive at nearly the same instant, within a fraction of a trillionth of a second. If the timing drifts, the interference fringes wash out and the information disappears. When everything is tuned, the combined system has a resolving power equivalent to a telescope as wide as the maximum separation between the telescopes that are linked. The result is not a pretty high-resolution photograph in the way you might expect from a regular camera. Interferometers usually detect patterns called fringes, bright and dark bands that vary as the system rotates with Earth or as engineers change the configuration. Reconstructing an image from those fringes is like solving a jigsaw puzzle where most of the pieces are missing. But even when the picture is incomplete, the details it reveals are sharp beyond anything a single mirror could hope to produce. At the Very Large Telescope, this means you can measure features billions of times fainter than what the human eye can see, and you can resolve angles so small it would be like picking out a pair of car headlights on the moon from Earth. One of the fields that benefits most from this precision is the study of planets around other stars. Exoplanets are faint, tiny, and buried in the glare of their host stars. Most of the time we detect them indirectly, by a wobble in the star or a slight dip in light as the planet passes in front. The Very Large Telescope has pushed further by directly imaging some young giant planets still glowing hot from formation, orbiting in dusty disks around their stars. Interferometric observations and advanced imaging instruments together can tease out the faint glow of a planet from the scattered light of the disk and track its orbit over years. That tells astronomers how massive the planet is, how far from its star it travels, and what the architecture of that newborn solar system looks like. The same machines have looked far beyond our own galactic neighborhood. One of the more subtle but profound uses of this observatory involved measuring the temperature of the universe billions of years in the past. The cosmic microwave background, the afterglow of the Big Bang, cools as the universe expands. Theory predicts exactly how that temperature should change with time. By using the Very Large Telescope to study the light from a quasar 11 billion light-years away, and analyzing how that light passed through carbon monoxide gas on its journey, astronomers could deduce how warm the background radiation was back then. The result matched the predictions very closely. It was a quiet triumph, a confirmation that the simple equations describing the cooling universe still held true deep in cosmic history. For an observatory built on solid rock, one of its most important battles is still with the air above it. The Atacama Desert is one of the driest places on Earth, which is perfect for infrared and visible astronomy. There's almost no water vapor to blur the view, and it has not rained on that mountaintop since records began. Yet even in that ideal air, hot rising currents and cold sinking pockets twist starlight as it passes down to the mirrors. The images on a detector will naturally shimmer and smear, just as the stars seem to twinkle to your naked eye. This is where adaptive optics enters the story, and it feels almost magical the first time you see it in action. The basic idea is to measure how the atmosphere is distorting the wavefront of incoming light in real time, then physically reshape a mirror to cancel that distortion. To get a reference, the observatory fires a powerful laser into the upper atmosphere. The beam excites sodium atoms left by meteor trails, making a tiny artificial star appear far above the telescope. By watching how that fake star twinkles, the system can infer how the air is bending light at that moment. Inside the telescope, a thin secondary mirror is mounted on thousands of tiny actuators. Dozens or hundreds of times each second, they push and pull on the glass, bending it by amounts measured in nanometers. The mirror becomes a living surface, wrinkling and relaxing constantly to keep up with the churning air. When the system is switched off, images blur. Turn it on, and a star shrinks into a tight, sharp point. Details in a distant galaxy that were smeared into a faint haze suddenly appear as crisp spiral arms, bars, and dust lanes. It is like putting on perfectly tailored glasses, except the lenses weigh several hundred kilograms and are controlled by computers instead of muscle. The combination of large mirrors, interferometry, and adaptive optics means that this desert observatory can sometimes surpass even famous space telescopes in sharpness at certain wavelengths. That does not mean ground-based instruments have replaced space-based ones. Space still has the advantage of total freedom from air and weather, and access to wavelengths that never reach the ground. But it does mean that the old hierarchy, where orbit always meant better, is gone. Instead, we have a more interesting landscape, where each platform has its own strengths, and many discoveries come from their partnership. Nowhere is that partnership clearer than in the long, patient work of watching the center of our own galaxy. For decades, radio telescopes had picked up a compact source of emission there called Sagittarius A star, hinting at some kind of energetic object buried in dust. The suspicion grew that a supermassive black hole lived there, but suspicion is not proof. To weigh that invisible object, astronomers needed to track the orbits of individual stars whipping around it, and that demanded acute vision through thick curtains of dust. Infrared light can penetrate that dust, and the Very Large Telescope, armed with adaptive optics, became one of the best tools for the job. Starting in the 1990s, teams of astronomers began to measure the positions of stars near the galactic center year after year. One star in particular, often called S2, drew attention. Its orbit brought it extremely close to the unseen mass at the center before flinging it back out again. By tracing that path over nearly 3 decades, researchers could apply the same gravity math used to weigh planets from their moons, but on a far more dramatic scale. The numbers pointed to an object with a mass about 4 million times that of our Sun, confined to a region smaller than our solar system. No cluster of normal stars, no ball of dark stellar remnants could fit those constraints without tearing itself apart. The simplest explanation was a single supermassive black hole. Even that was not the end of the story. General relativity, the theory of gravity formulated by Albert Einstein, predicts that orbits in a strong gravitational field do not close into perfect repeating ellipses. They precess, the point of closest approach, slowly rotating like the wobble of a spinning top. As instruments on the Very Large Telescope improved, astronomers eventually detected this relativistic precession in the path of S2. They also measured subtle changes in the wavelength of its light as it fell in and climbed back out of the deep gravitational potential. Together, these observations were a high-precision test of general relativity in one of the strongest gravity environments available to us outside a black hole itself. Once again, the theory passed. It is striking to realize that some of the most convincing evidence for the existence of a supermassive black hole at the heart of the Milky Way did not come from a gleaming space observatory, but from a set of machines bolted to a rocky summit surrounded by sand and dust. Those machines had to survive temperature swings, high winds, and the constant threat of fine dust infiltrating every crevice. Each unit telescope weighs about 430 tons, roughly as much as a fully loaded jumbo jet, yet it can swivel with astonishing smoothness, controlled by motors so precisely balanced that a push from a human hand on the right lever would slowly move the entire structure. The engineering that makes this possible is a quiet marvel. The telescopes rest on hydrostatic bearings, thin layers of oil that allow hundreds of tons of steel and glass to glide almost friction-free. Their drives compensate for the rotation of Earth so that a distant star stays perfectly centered for hours. Vibration from wind gusts and mechanical motion has to be damped and filtered out. Mirror surfaces are routinely cleaned and recoated, often on a schedule that feels more like medical care than maintenance. Underneath, a network of cooling systems, power lines, control cables, and optical fibers feeds the whole organism. The Very Large Telescope is less a single instrument and more a living ecosystem of technology, tuned to the edge of what the site and the planet will tolerate. Of course, all this complexity comes with vulnerability. The desert is dry, but dust storms can sweep across the mountain, forcing the domes to close. Earthquakes are a constant background threat in Chile, and the structures are designed to ride them out without cracking mirrors or jamming gears. Logistics are intense. Everything from delicate detectors to cleaning solvents and food for staff has to be trucked up the mountain. And while the site feels like a fortress under the stars, it exists within the constraints of national funding agencies, international collaborations, and the shifting priorities of science. Instruments are proposed, built, used, and eventually retired when better ideas come along. Still, the payoff for this effort is enormous. Night after night, the Very Large Telescope contributes to a flood of discoveries that reach far beyond black holes and exoplanets. It has helped detect freshly forged elements in the debris of neutron star collisions. It has traced the motions of gas in distant galaxies to understand how star formation has changed over cosmic time. It has mapped the winds blowing off massive stars and probed the dusty cocoons where new stars are being born. Many of those results then feed back into the design of future projects, shaping the questions that the next generation of observatories will ask. If you zoom out a bit, you can think of this desert summit as the ground-based counterpart to the famous telescopes in space. When a space observatory spots something strange or interesting, ground-based instruments like this one often rush to fill in the details with sharper spectra, longer monitoring, or different wavelengths. When the Very Large Telescope finds something unexpected, it can trigger follow-up observations from satellites and space telescopes that see energy bands the ground cannot. Each platform depends on the others, and no single machine tells the full story. And yet, as powerful as a focused observatory like this is, there is a hidden limitation in the way it looks at the sky. These telescopes stare deeply at one small patch of space at a time. They are like someone peering through a keyhole, studying whatever passes that narrow line of sight in exquisite detail, while the rest of the house goes unseen. What happens if, instead of staring at one target, you try to watch the whole sky in motion, catching every transient event, every new explosion, every wandering rock that happens to cross our cosmic neighborhood? That question leads to a very different kind of eye on the universe, one that does not just take pictures, but films the sky over and over again. If you want to film the sky over and over again, you first have to understand something strange about the way the sky keeps time. Every point of light above you is not just a place, it is a when. Light takes time to travel, and the farther away something is, the further back in history we see it. When you look at the moon, you see it as it was about 1 second ago. When you look at the sun, you see it as it was a little more than 8 minutes ago. The nearest big galaxy, Andromeda, appears to you as it was more than 2 million years in the past. So when astronomers talk about building bigger and more sensitive telescopes, they are not just trying to see farther out in space. They are trying to build honest-to-goodness time machines. Imagine you stand in a field at night, holding a candle while a friend walks away. At first, the candle stays bright. After a few hundred steps, it looks smaller and dimmer until it becomes a pinprick and then vanishes into the darkness. Nothing happened to the candle, but its light spread out. The same thing happens with stars and galaxies. Light fans out like an expanding sphere, and every extra step in distance means fewer photons reach your eye. On top of that, clouds of gas and dust between you and the source can scatter or absorb a lot of that light. By the time it reaches us from the first galaxies, their glow is incredibly faint, smeared and stretched by distance, dust, and the expansion of space itself. That expansion is the next twist in our story. After the Big Bang, space did not just sit there quietly. It swelled, and has been swelling ever since. As light waves ride that expansion, their wavelengths get stretched. Blue light becomes redder, then slips into the infrared, then into microwave and radio bands. Astronomers call this redshift, and it means that the earliest galaxies are now brightest not in the visible light that human eyes evolved to see, but in infrared light, the same range we usually associate with heat. If you try to see those galaxies with a visible light telescope, you get almost nothing. You need a giant, incredibly cold infrared eye. Meanwhile, the universe has been busy hiding things behind dust. Star-forming regions, the crowded centers of galaxies, and the disks where planets assemble around young stars are full of fine grains that scatter and absorb visible light. Infrared light tends to slip through those clouds much more easily, so an infrared telescope does double duty. It can see the oldest, most redshifted galaxies, and it can peer through otherwise opaque regions to watch stars and planets in the making. In the 1990s, engineers and scientists at the American Space Agency started sketching out what it would take to build a truly powerful infrared observatory in space. For years, they had been thinking about a successor to the Hubble Space Telescope, something they initially called the Next Generation Space Telescope. On paper, it looked almost simple: an 8-meter mirror, an orbit in deep space, and a budget measured in the hundreds of millions of dollars. As they worked through the details, reality pushed back. The mirror had to be light enough to launch and strong enough to hold its shape at cryogenic temperatures. The detectors had to work far out in the infrared. The whole system had to be insulated from heat coming from the sun, from Earth, and even from its own electronics. The numbers and the complexity grew, and the mission evolved into what we now know as the James Webb Space Telescope. To understand why this new telescope had to be so different, it helps to compare it with Hubble. Hubble is roughly the size of a bus, with a primary mirror about 2.5 meters across. It orbits a few hundred kilometers above Earth, whipping around the planet every 90 minutes. It sees mostly invisible and ultraviolet light, with a little reach into the near-infrared. It was designed to be serviced by astronauts, and over its long life, it has had cameras swapped out, gyroscopes replaced, and even its famously flawed mirror corrected. The James Webb Space Telescope aimed to do something that Hubble simply could not. It needed to collect much more light at longer wavelengths, and it needed to live in a much colder, darker, more distant place. That is why its primary mirror is about 6.5 meters in diameter, giving it a collecting area roughly 6 times larger than Hubble's. Instead of a single solid piece of glass, the mirror is made of 18 hexagonal segments of beryllium, each coated in a thin layer of gold. Beryllium is stiff, light, and stable at low temperatures. The hexagonal piles fit together like a honeycomb to form a big, nearly circular eye. Each segment sits on small actuators that can tilt and flex it by tiny amounts, allowing engineers to tune the mirror in space so that all the segments act as one precise surface. The orbit is even more unusual. Rather than hovering close to Earth, the James Webb Space Telescope travels out to a spot about 1.5 million kilometers away, in the direction opposite the Sun. This region, called the second Lagrange point, is a place where the gravity of Earth and the Sun and the motion of the telescope all balance so that it can stay in step with our planet as we go around our star. From there, the telescope always sees Earth and the Sun in roughly the same direction. That might sound like a minor detail, but it is the key to one of the most important parts of the design, the sun shield. Infrared detectors are basically heat detectors. To see faint cosmic heat, your own hardware has to be colder than the things you are looking at. Any stray warmth from the spacecraft itself would flood the instruments with unwanted infrared light. To keep the optics and detectors down near 223 degrees below zero on the Celsius scale, engineers wrapped the whole thing in a multi-layered shield about the size of a tennis court. It is made of 5 layers of a high-tech plastic called Kapton, each layer coated with reflective metal and spaced a little apart from the next. The sunward side faces the Sun, Earth, and Moon and heats up. The shadowed side, where the telescope and instruments sit, radiates heat away into deep space and cools down to the temperatures the detectors need. There is a catch. A shield the size of a tennis court and a mirror wider than the inside of most rockets cannot simply be launched in their working shape. The entire observatory had to be designed as a kind of giant piece of origami. The mirror folds its side wings back. The sun shield folds and wraps around the central structure. Booms, pallets, covers, and protective layers are all tucked in. During launch, the whole telescope rides in a compact configuration atop a heavy-lift rocket. Only once it is safely in space does it begin its slow unfurling into its final form. At every stage of this design, the mission was a tug-of-war between ambition and fear. On the ambitious side were the science goals. See the first galaxies forming a few 100 million years after the Big Bang. Trace how stars and planets assemble inside dusty cocoons. Read the chemistry of exoplanet atmospheres to look for water, methane, carbon dioxide, and other markers of interesting physics and perhaps even biology. On the fearful side was the long list of ways everything could go wrong. Hundreds of mechanisms had to fire in the right order. Each cable release, each hinge, each latch was a potential single point of failure. Once the telescope reached its distant orbit, no astronaut with a toolbox could drop by to fix anything. The story of its budget and schedule tells you just how hard it was to reconcile those two sides. In its early planning days, the mission was pitched with a price tag of around $500 million. As the design matured, as engineers discovered new problems, and as tests revealed weaknesses, that estimate climbed. By the mid-2000s, cost growth and delays were already causing concern. Around 2011, after a series of technical setbacks and rising expenses, lawmakers seriously considered canceling the project altogether. For a time, it looked like 2 decades of work might end with nothing ever leaving the ground. What saved the telescope was a combination of scientific consensus and public pressure. In the community of astronomers, decadal surveys, which are big priority-setting studies, had ranked this mission at the very top of the wish list for space astrophysics. It was not just one more telescope, it was the key step to answering basic questions about how the first structures in the universe formed. Outside that community, the idea of a giant golden space telescope that could see back almost to the beginning of time had captured imaginations. Canceling it would not just disappoint scientists, it would be a very visible retreat from a bold exploration promise. Even so, the final bill landed near $10 billion, and the schedule slipped by more than a decade. Each delay brought new rounds of testing. A tear in a sunshield layer had to be understood and prevented from happening again. Vibration tests on critical hardware revealed bolts that were not tight enough, or supports that needed redesign. Teams rehearsed the deployment sequence over and over on the ground, knowing that in space, there would be no second chance. Every step forward was paid for in nights of anxiety for engineers and scientists who had dedicated their careers to this one machine. When launch day finally came, near the end of 2021, many of those people watched from the control rooms of the European spaceport in French Guiana, from mission centers back home, or from their living rooms with family. You can picture that moment if you like. A silent rocket on the pad in the early light, a countdown ticking toward zero, then the sudden, controlled violence of ignition. The ascent took only minutes, but it carried with it decades of work and billions of dollars. When the fairing opened and the telescope separated, there was a sense of collective held breath around the world. Then came the long, nerve-stretching deployment on the way out to the Lagrange point. First, solar panels unfolded to supply power. Then the sun shield pallets lowered, covers rolled back, membranes unwrapped, and tensioning cables pulled each of the 5 layers into its carefully separated position. After that, the secondary mirror swung into place on its tripod-like support, followed by the gradual unfolding and locking of the primary mirror wings. Each step sent data back to Earth. Each green confirmation on a screen meant one less thing to worry about. Yet it was only when all the mechanisms had done their jobs and the optics had cooled and been painstakingly aligned that the real question could be asked. Did the universe look any different through this new eye? The first test images, released during commissioning, already told the answer. Stars appeared as pinpoint-sharp crosses, each one a confirmation that the mirror segments were working together as one. Background galaxies, which had been faint blobs in earlier telescopes, suddenly showed delicate arms, clumps, and warped shapes. When the first official images and spectra were unveiled in mid-2022, the effect on both scientists and the public was electric. A deep-field image revealed thousands of galaxies in a patch of sky smaller than a grain of sand held at arm's length. Some of them likely formed when the universe was less than 1 billion years old. Other views showed towering pillars of gas and dust lit by newborn stars, and the faint, distinctive pattern of molecules in the atmosphere of a hot Jupiter exoplanet. With those images, the James Webb Space Telescope fulfilled its promise as a time machine. Light that had left its source billions of years ago, long before Earth existed, finally ended its journey in a set of gold-plated mirrors and infrared detectors, then in downlink antennas, then in data servers, then in the eyes of people looking at screens. As we keep using this telescope, new puzzles have emerged. Some of the earliest galaxies it sees look more massive and more luminous than many models of galaxy formation had predicted. Star formation in the young universe may have been more intense and efficient than we thought. It is too early for any final verdicts, but you can feel that our simple picture of cosmic history is being sharpened and in places challenged by the flow of new observations. At the same time, the telescope is living up to its other roles. It has dissected disks around infant stars, revealing rings and gaps where planets may be carving paths. It has taken spectra of several exoplanet atmospheres, finding water vapor, carbon-containing gases, and hints of clouds and hazes. It has traced the chemistry of the interstellar medium, the thin gas and dust that fill the space between stars, showing how complex molecules arise long before they end up in planets or living things. All of this comes from staring intensely at small patches of sky, often for many hours at a time, building up faint signals, photon by photon. This is the paradox of a time machine telescope. It dives incredibly deep, but only through a very narrow straw. Most of the sky is still unmonitored. If a star explodes as a supernova on the far side of the Milky Way, or a small but dangerous asteroid slips into a trajectory that will cross Earth's orbit, the James Webb Space Telescope will not notice unless someone else spots it first and calls for a targeted observation. To turn our understanding of the universe from a collection of still photographs into an actual movie of change, we need another kind of observatory, one that can sweep the entire sky again and again, catching everything that flickers, flares, or moves, while telescopes like Webb and the Very Large Telescope zoom in for close-ups. When you want to film the changing sky, rather than stare at one small patch, you need a very different kind of eye. Instead of a narrow straw peering deep into the past, you want a wide lens that can sweep overhead again and again, catching anything that flares, fades, or moves. For years, astronomers had dreamed about such a machine, something that could turn the entire visible sky into a kind of cosmic time-lapse. On paper, that dream looks simple. In practice, it turns into one of the most ambitious ground-based observatories ever built. That machine now has a name that carries its own history. It is called the Vera Rubin Observatory, in honor of Vera Rubin, the astronomer whose careful measurements of galaxy rotation curves helped reveal the existence of dark matter. The observatory itself stands on a Chilean mountaintop, not far from other big telescopes we have met. That location is no accident. The Atacama region offers clear, dark, dry skies for much of the year, with little light pollution and high-altitude air. It is about as close to a natural, planet-wide observatory as Earth can offer without leaving the ground entirely. The heart of this new eye is a telescope with a mirror about 8.4 meters across. That is already large, but what really sets it apart is the way it bends and focuses light. It uses a clever three-mirror design that provides a huge field of view while keeping optical distortions under control. Imagine a camera so wide that each exposure captures an area of sky roughly 40 times the size of the full moon. Now imagine taking that picture with a sensor so detailed that you could resolve a distant city block if the telescope were pointed at Earth. That is the scale we are talking about. Mounted at the focus of this optical system is the real star of the show, a camera with about 3.2 billion pixels. It is often described as the largest digital camera ever built for astronomy. If you tried to display one of its images at full resolution on an ordinary high-definition television, you would need thousands of screens tiled together. Each exposure is rich enough that you can zoom in again and again, finding fainter and smaller objects hiding in the background, like a fractal where structure appears every time you look closer. What makes this observatory special is not just how big and sharp each image is, it is how often those images will be taken. The survey strategy is simple and ruthless. Point at a patch of sky, expose for about 15 seconds, shift slightly, expose again. Repeat this pattern all night, every clear night. Over the course of a few nights, the telescope will have imaged the entire accessible sky. Then it will start again. Night after night, year after year, it will build up a stack of images for every point it can see. The result will be a moving picture of the universe, stretching over a decade. You can already feel what this means. In that movie, anything that changes will stand out. A supernova in a distant galaxy will flare up and fade away. A small, near-Earth asteroid will glide from one position to another, its motion betrayed by two slightly offset points of light in the short gap between exposures. A quasar will slowly brighten and dim as gas spirals into the hungry black hole at its core. Even subtle effects, like the way gravity from a moving object slightly magnifies a background star in an event called microlensing, can leave a fingerprint in the data if you watch patiently enough. Because of that, the Vera Rubin Observatory is designed around a few key science goals. One is to understand the nature of dark matter and dark energy by mapping how galaxies and clusters are distributed in 3 dimensions and how that distribution changes over time. Another is to take a census of the solar system's small bodies, especially near-Earth asteroids larger than about 140 meters. Those are big enough that if one hit our planet in the wrong place, it could devastate a region or a city. A third goal is to study the variable universe, everything from flickering stars to explosive transients that last only days or hours. There is also a powerful connection to the new world of gravitational wave astronomy. Facilities like the Laser Interferometer Gravitational Wave Observatory, which listens for tiny ripples in spacetime from colliding black holes and neutron stars, can tell us roughly where in the sky an event happened, but not with pinpoint precision. Their alerts cover patches of sky that can be dozens or hundreds of times the full moon. A telescope that can sweep large areas quickly is the perfect partner. When a gravitational wave alert goes out, the Rubin camera can comb that region, looking for a new point of light that was not there before. That glow might be the kilonova, the radioactive debris flare, from a neutron star merger. Catching it early lets astronomers watch how heavy elements like gold and platinum are forged and blown into space. All that science comes with a brutal data cost. Each 15-second exposure produces an image of tens of gigabytes. Over one long night, the observatory can generate many terabytes of data. Over a year, it will accumulate something like 1,000,000 gigabytes, a volume that would fill a wall of hard drives. Handling that flood is as central to the design as the mirrors and the dome. The raw bits have to be processed quickly to produce alerts for new or changing objects, archived reliably for long-term study, and made accessible to researchers around the world. To manage this, the observatory will rely on high-speed data links that move images from the mountaintop to data centers in real time. There, pipelines automatically subtract previous images of the same patch of sky to highlight changes. The software must decide in seconds whether a new point of light is likely to be a real astrophysical event or a glitch. When it finds something interesting, it sends out an alert that other telescopes can respond to. In essence, the Rubin Observatory acts as the universe-wide smoke detector and switchboard, spotting things as they happen and pointing more specialized instruments toward them. It is worth pausing on just how global and collaborative this effort is. The project is overseen by the Association of Universities for Research in Astronomy. It has support from national science agencies and private partners. It was ranked as the top ground-based priority in a major astronomy planning exercise around 2010, which helped secure long-term funding. Building it has meant years of work by engineers, software developers, opticians, and construction crews spread across several countries. Each component, from mirror segments to camera sensors, had to survive its own gauntlet of design revisions and tests before making the long trip to the Chilean site. The camera itself might be the most visually striking example. Its focal plane is a mosaic of dozens of individual charge-coupled device sensors, each a high-quality detector in its own right. They have to sit in a carefully controlled environment, cooled to reduce thermal noise, but not so cold that they become brittle or unstable. The system must remain aligned to fractions of the width of a human hair, while the entire telescope slews rapidly from one patch of sky to another. A shutter has to open and close reliably many times per minute for years. Filters that select different bands of wavelength must slide into place without jamming. Any failure in that chain risks downtime in a survey whose power comes from relentless repetition. There's a quieter engineering challenge too. The telescope's mount and dome have to be nimble. The structure must accelerate, point, settle, and be ready for a sharp image in seconds. That is very different from the slow, almost stately tracking of some older observatories that might stare at a single target all night. Yet the motion has to be smooth enough that vibrations do not blur the view. The dome itself must open in a way that minimizes turbulent air spilling across the mirror, and the entire site has to manage its own sources of light and heat so as not to pollute its own images. As you listen to this, you might be picturing a triumphant machine that simply turns on and starts delivering pure discovery. Reality, as usual, is more mixed. One of the biggest threats to a wide-field ground-based survey was barely on the radar when the project was first planned. It is not weather, it is not earthquakes, though those are also a concern in Chile. It is the growing swarm of bright satellites in low Earth orbit. 10 years ago, a deep image might catch an occasional streak from a passing spacecraft. Today, with plans for tens of thousands of communications satellites, that streaking can become almost constant at certain times of night and certain seasons. For an observatory that depends on clean, repeated imaging of the same patches of sky, those bright trails are a serious problem. They can saturate the detectors along their path, leaving scars in the data. They complicate automated software that tries to identify real astrophysical changes. Teams are working on mitigation strategies. Satellite operators have experimented with darker coatings and lower reflectivity designs. Software pipelines are learning to recognize and mask satellite trails. Survey schedules can be tuned to avoid the worst congestion when possible, but there is no perfect fix. The simple truth is that low Earth orbit is becoming crowded, and that crowding spills into the work of ground-based astronomy. This tension between human activity in orbit and our desire for a quiet sky opens up a bigger question. How do we balance the commercial and social benefits of global broadband networks with the scientific value of an unobstructed view of the universe? The Rubin Observatory sits right on that front line. Its engineers and scientists find themselves not just building hardware and software, but also arguing for policies, brightness limits, and cooperation from satellite companies. The outcome will not only shape this survey, but also the feasibility of future sensitive telescopes on the ground. Despite these challenges, the potential payoff remains huge. Over a 10-year survey, the Rubin dataset will let astronomers map how galaxies cluster and stretch under the influence of dark energy, improving our measurements of how the universe expands. It will reveal streams of stars, remnants of ancient dwarf galaxies that were torn apart and digested by the Milky Way, helping us reconstruct the assembly history of our own galaxy. It will build the most complete inventory yet of faint, distant solar system objects, from trans-Neptunian bodies to near-Earth rocks, giving planetary defense efforts more time to react if something dangerous is found on a collision path. If you think back to the patient staring of the Very Large Telescope or the deep drilling gaze of the James Webb Space Telescope, there is a pleasing symmetry here. Those telescopes are like microscopes, able to zoom in on a single specimen in extraordinary detail. The Rubin Observatory is more like a wide-angle security camera that watches everything at once and calls attention to anything out of the ordinary. Each depends on the other. Without deep follow-up, many transient discoveries would remain mysterious blips. Without wide surveys, many targets for deep study would never be found. Once you see that pattern, you may also see what is still missing. We have telescopes that can film the sky and telescopes that can stare deeply into narrow fields. We have sophisticated ways to combine small mirrors into virtual giant eyes. Yet there is a simple, almost brutal idea that still pushes at the edges of possibility. What if you simply built one mirror that is enormous, far larger than anything we have now, engineered in segments but acting as a single coherent surface, and placed it on a mountaintop designed to support thousands of tons of moving glass and steel? What new levels of detail would that unlock in distant galaxies, in the atmospheres of exoplanets, in the orbits of stars around black holes? On paper, that idea sounds almost naive. Take the logic that bigger mirrors gather more light and reveal finer detail, then push it as far as the laws of engineering and geology will allow. In reality, it becomes a puzzle made of glass, steel, and gravity. If you tried to build a single solid mirror 40 meters wide, it would sag under its own weight. Temperature changes would warp its shape. Transporting it up a mountain would be impossible. The only way forward is to cheat. You build a giant mirror out of hundreds of smaller ones, teach them to behave as a single surface, and wrap the whole thing inside a moving building the size of a sports stadium. That is the vision behind the extremely large telescope rising on Cerro Armazones in Chile. The name once again sounds like astronomers ran out of poetry and reached for the obvious, yet it is accurate. When finished, its primary mirror will be about 39 meters in diameter. For comparison, that is wider than a basketball court. The surface will not be one piece. It will consist of almost 800 hexagonal segments, each a little over 1 meter across, tiled together like scales. Each segment is mounted on actuators that can nudge it in and out and tilt it a tiny amount. The whole system has to be kept aligned to better than the width of a human hair. The telescope uses more than one mirror to do its job. Light from the sky first hits the giant segmented primary mirror, then bounces up to a smaller secondary mirror, then down again to other optical elements before finally reaching the instruments. This multi-mirror design allows the telescope to fold the light path into a more compact structure and to correct for distortions at several stages. One of the mirrors in that chain, often called an adaptive mirror, is thin and flexible, supported by thousands of little actuators. Like the adaptive optics systems at the Very Large Telescope, it will bend and ripple many times per second to cancel out atmospheric turbulence, but on a much grander scale. The structure that holds all this glass is itself an enormous machine. The main mount will weigh thousands of tons, yet it has to track stars smoothly as Earth turns, with errors so small that they would be hard to see with the naked eye at arm length. The dome that encloses it is more like a rotating building than a traditional telescope housing. It needs to open large vents and shutters to let the air inside and outside equalize, reducing turbulence while still protecting the optics from wind gusts and sudden changes in temperature. All of this sits on a mountain that had its top literally cut off to create a flat platform, which had to be stabilized against the earthquakes that run through the Andes region. Why go to this trouble when we already have powerful telescopes on the ground and in space? One reason is simple sensitivity. A mirror with a collecting area of more than 900 square meters can gather far more light than any of its predecessors. That allows it to study much fainter objects, or to reach the same level of detail in less time. Another reason is resolving power. The larger the mirror, the finer the details it can distinguish, especially when combined with advanced adaptive optics. With that kind of acuity, this telescope aims to look not just at stars and galaxies, but at structures within them that have been out of reach. One of the most exciting targets lies in the growing field of exoplanet science. We already know of thousands of planets around other stars, but most of those are detected indirectly. They tug on their stars or block a bit of starlight as they pass in front. Directly imaging an exoplanet, especially one that is small and cool like Earth, is extremely hard. The glare from the host star overwhelms the faint reflected light from the planet. A gigantic, well-corrected telescope can use devices called coronagraphs and other high-contrast techniques to suppress the star and reveal the planet. By spreading the tiny amount of light from that planet into a spectrum, astronomers can study its atmosphere for gases such as water vapor, oxygen, methane, and carbon dioxide. The idea of reading the air of distant worlds is more than a technical challenge. It touches a basic human question about whether life is common or rare in the universe. No single observation will settle that question, and the presence of familiar molecules does not automatically mean biology is at work. Yet a telescope like this can start to gather statistics. It can look at many planets around different kinds of stars at different distances from their suns and build up a sense of how varied their atmospheres are. That will feed back into models of how planets form and evolve, and of how fragile or robust habitable conditions may be. Another arena where such a giant eye can make a difference is at the centers of galaxies. We already saw how the Very Large Telescope helped weigh the black hole at the core of the Milky Way by tracking the orbits of nearby stars. Scale that trick up. With a much larger mirror and sharper vision, this new observatory can watch stars in other galaxies dance under the influence of their central masses. It can probe closer in toward event horizons. It can measure how gas flows, how jets from active galactic nuclei interact with their surroundings, and how feedback from supermassive black holes shapes the growth of galaxies. This speaks to a deeper theme in modern cosmology. We have mathematical models that describe how the universe expands, how structure grows, and how gravity behaves on large scales. Those models rely on ingredients like dark matter and dark energy, whose nature we still do not fully understand. To test them, we need detailed measurements of how gravity acts in dense environments, not just in the smooth, large-scale average. A telescope that can resolve individual stars and gas clouds in distant galaxies gives us more precise tracers. It lets us see whether they move exactly as expected under general relativity and our current dark matter models, or whether there are subtle deviations that might hint at new physics. The extremely large telescope will also push into the field of galaxy evolution at early times. Even with instruments like the James Webb Space Telescope, much of the distant universe appears as faint smudges. With a huge collecting area, the new giant can obtain high-quality spectra of those smudges, turning them from dots into physical objects with measured motions, chemical compositions, and internal structures. By comparing young galaxies at different ages, astronomers hope to reconstruct how they assembled, how quickly they turned gas into stars, and how their central black holes grew alongside them. None of this will be simple. The instruments that sit at the focus of the telescope are complex devices in their own right. Some are designed to take spectra of thousands of objects at once by feeding starlight into bundles of optical fibers. Others use integral field units that record a spectrum at every point over a small patch of sky, building a three-dimensional data cube where 2 dimensions are position and the third is wavelength. The data rates will be enormous, and the analysis will require advanced software and large computing clusters. In that sense, this telescope is as much a data factory as a light collector. For all its grandeur, the project is also vulnerable in familiar ways. Construction in a remote desert depends on steady funding, stable politics, and safe working conditions. The global pandemic that began in 2020 caused delays as supply chains were disrupted and work crews had to adapt. Costs have climbed and schedules have shifted. When you push to this scale, there is little room for redundancy. A problem with a major mirror segment supplier, a delay in delivering the adaptive mirror, or a hiccup in integrating the dome can ripple through the timeline. There is also a quiet race in the background. Other groups are working on their own giant telescopes, such as the 30-meter telescope and the Giant Magellan Telescope. Each has its own design philosophy and site, and each has faced its own technical and social challenges, including protests over land use and cultural concerns. Together, these projects represent a kind of arms race of peaceful discovery. Whichever ones come online first and perform as advertised will define the high-resolution view of the cosmos for decades. The Extremely Large Telescope is one of the leading contenders, but it is not alone, and that competition pushes everyone involved to refine their designs and their science cases. If you imagine standing on the mountain when the telescope finally opens its eye, you might picture a moment of quiet awe as the first light from a distant star reflects off hundreds of mirror segments and converges at a detector. Yet the real story will be slower and more deliberate. There will be months of alignment, calibration, and test observations. Engineers will tweak the positions of mirror segments and the behavior of actuators. Scientists will tilt and focus and check that what they see matches both the laws of optics and the expectations from known targets. Only then will the observatory settle into its rhythm of nightly operations, joining the network of instruments that collectively watch the universe. Once it does, its most profound impact may not come from spectacular images that make the news, though those will certainly arrive. It may come from precise measurements that quietly build up over years. Slight shifts in the wavelength of light from distant galaxies that tighten constraints on dark energy. Tiny wobbles in the paths of stars near black holes that test the edges of general relativity. Subtle differences in exoplanet spectra that tell us which atmospheres are cloudy and which are clear, which are rich in certain gases and which are depleted. These are the kinds of clues that do not shout but whisper, drawing patient listeners toward deeper understanding. If you step back from the details, a pattern emerges across all the telescopes we have talked about. Each one is a kind of extreme solution to a specific problem. The Very Large Telescope and its cousins fight the atmosphere with lasers and flexible mirrors. The James Webb Space Telescope flees heat and air entirely, hiding behind a sunshield millions of kilometers from Earth. The Rubin Observatory embraces the entire sky, trading narrow depth for broad coverage to watch for change. The Extremely Large Telescope bets on raw size and exquisite control to peel new details from faint light. Taken together, they show that there is no single way to see the universe. There are only clever ways to work around nature and our own limitations. Yet, even after carving mountaintops into platforms and building domes that move like giant machines, we are still tied to the ground. The air above us, no matter how carefully corrected, always blurs and blocks certain wavelengths. Space telescopes break free of that, but they are limited in size by rockets and in lifetime by fuel and hardware fatigue. Somewhere between those extremes lies another path. If you cannot put a stadium-sized observatory into orbit, you might instead lift a smaller but still powerful telescope into the stratosphere, above most of the atmosphere, yet still within reach of people and planes. To see how that idea plays out, you have to walk down a runway toward a very unusual aircraft with a hole in its side. From a distance, it almost looks like any other wide-body jet sitting at the edge of a runway. White fuselage, swept wings, a row of passenger windows. Then you walk closer and notice the oddity that should not be there. Near the tail, on one side, the smooth skin of the aircraft is broken by a massive sliding door. When it opens in flight, it reveals not passengers but a telescope mirror, staring sideways into the night sky. This is the Stratospheric Observatory for Infrared Astronomy, and it sits at a strange crossroads. It is part aircraft and part observatory, part engineering triumph and part cautionary tale about the cost of pushing telescopes into unusual places. The idea of putting telescopes on airplanes did not begin with this jumbo jet. Astronomers had long known that many of the most interesting wavelengths of light are absorbed by Earth's atmosphere before they reach the ground. Water vapor and carbon dioxide in particular are very good at blocking infrared. That is great for life since it helps regulate temperature, but frustrating if you are trying to study the cool dust around forming stars or the faint glow of complex molecules in interstellar space. One way around this is to go high. Rocket-borne telescopes and high-altitude balloons can poke briefly above most of the water vapor. In the 1970s and 80s, NASA flew the Kuiper Airborne Observatory, a telescope in a modified cargo plane to chase eclipses and observe objects in infrared bands that were otherwise impossible to reach. Those early experiments taught two important lessons. First, flying above most of the atmosphere really does open a new window on the universe. Second, doing precision astronomy from a vibrating metal tube that is hurtling through turbulent air is difficult. Every jolt from the engines, every tiny flex in the airframe shakes the telescope. Stabilizing it enough to keep a star centered on a detector requires gyroscopes, isolation systems, and careful control of airflow in and out of the open cavity. Yet the promise of a mobile infrared observatory was strong. You could take it to whichever hemisphere suited your target. You could upgrade instruments on the ground. You could schedule flights around specific events, like a distant planet passing in front of a star. Out of that promise grew a more ambitious project. In the 1990s and 2000s, NASA and the German Aerospace Center partnered to build a new flying telescope on a larger platform. They chose a Boeing 747 short-body aircraft, a version with extra range and a slightly smaller fuselage. Engineers cut a large door into the side near the tail and installed a 2.7-meter reflecting telescope on a sophisticated mounting system. At cruising altitude, that door could slide open, exposing the mirror directly to the sky, while the rest of the cabin remained pressurized and comfortable for scientists and crew. Operating in the stratosphere at 11 to 13 kilometers above sea level, this observatory soared above about 90% of the water vapor in the atmosphere. That dramatically reduced the infrared absorption that plagues ground-based telescopes. Wavelength bands that are entirely blocked at sea level become accessible. Lines from water molecules in star-forming regions, spectral features from complex organic molecules, and the faint thermal glow from dust and cold gas all become clearer. In a sense, the aircraft carved out a new kind of observing site, a high-altitude island of clarity that could be parked above almost any part of the globe. Of course, no piece of hardware this unusual is simple to operate. The telescope sat on a bearing that allowed it to swivel with minimal friction, isolated from much of the vibration of the airframe. Gyroscopes sensed any motion and helped the system compensate. The outboard side of the telescope, the one exposed when the door opened, had to deal with supersonic air rushing past the cavity. Engineers shaped the opening and the baffles around it so that the air would flow smoothly instead of setting up roaring resonances that could shake everything apart. The cavity itself had to be cooled and controlled so that heat from the aircraft would not flood the detectors with unwanted infrared light. Inside, the working environment felt more like a small laboratory than a passenger flight. Racks of instruments and control computers filled the cabin. Scientists sat at consoles, watching data scroll in real time. Pilots followed carefully planned routes that were often dictated more by where the telescope needed to point than by the usual efficiencies of air travel. A typical flight might take off in California, climb to altitude, and then fly long, slow legs over the Pacific, turning the entire aircraft to keep a distant nebula or galaxy in the telescope's narrow field of view. What did all this buy in terms of science? Quite a lot. The observatory studied star formation by looking at the infrared glow of dust and gas in regions where massive stars are being born. It mapped magnetic fields in our galaxy by measuring how alignment of dust grains polarizes emitted light. It peered into the dense, cold centers of molecular clouds where future stars and planets take shape. It examined the chemistry of planetary atmospheres, both in our solar system and beyond, by watching how starlight and sunlight interact with those gases at wavelengths that ground-based observatories cannot reach. One of the more striking results involved the detection of a molecule called helium hydride in space. This simple ion, made of a helium atom and a proton, is believed to be one of the first types of molecules to form in the universe after the Big Bang, when the first atoms were cooling and combining. For decades it had been predicted but not clearly seen in interstellar space. The flying observatory finally turned its mirror toward a planetary nebula where conditions were right, and found the spectral signature that matched the expectations. It was a small but satisfying confirmation of a piece of early universe chemistry, made possible only because of access to a specific far infrared band. At other times, the aircraft chased more dramatic targets. When dwarf planet Pluto passed in front of a distant star, the way the starlight dimmed and reappeared could reveal details about Pluto's thin atmosphere. To catch that alignment, observers needed to be in a particular narrow path on Earth where the occultation would be visible. A mobile observatory in the sky could fly directly into that path. By placing itself under the shadow track and watching with sensitive infrared instruments, it helped refine measurements of atmospheric pressure and temperature around a world billions of kilometers away. The observatory also tuned its mirror toward young planetary systems, where comets and asteroids collide, grinding themselves into dust. Infrared observations at high altitude can pick out the glow of that dust and its spectral fingerprints, telling scientists about its composition and grain size. These are the raw materials of planets. By comparing disks around different stars, astronomers can test ideas about how common certain building blocks are, and how quickly they evolve from chaos into stable planetary arrangements. In some ways, the most intangible contribution of this flying telescope was not any single discovery, but the development of new techniques. Stabilizing a large mirror in a moving aircraft, dealing with the aeroacoustics of an open cavity at high speed, integrating complex cryogenic instruments into a platform that experiences constant vibrations. All of these pushed engineering in directions that benefited other projects. Students and early career scientists could get hands-on experience in an observatory that, unlike a satellite, they could literally walk into, tinker with, and upgrade between flights. For all its ingenuity, though, the project carried a heavy load of costs and constraints. Flying a large jet regularly is expensive. Fuel, maintenance, crew, and infrastructure for hangars and runways add up. Every hour in the sky came with a price tag, and the number of hours was limited by budgets. Weather also mattered. Although the aircraft could climb above clouds, storms and high-altitude winds could disrupt plans or force changes in flight paths. The need to operate from suitable airfields with long runways constrained where it could be based. Over time, a hard question began to loom. Was the scientific return from this mobile infrared observatory keeping pace with its expense, especially as space-based infrared telescopes like the Spitzer Space Telescope and later the James Webb Space Telescope came online? Flying above most of the atmosphere opened bands that ground-based telescopes could not reach, but spaceborne observatories did even better. They lived above all of the atmosphere and could stare for hours without the complications of flight schedules and aircraft safety. Independent reviews eventually concluded that while the flying telescope was producing solid science, its output per unit cost lagged behind other major facilities. As budgets tightened and new missions competed for funding, pressure grew to redirect money toward projects that could deliver more discoveries for the same investment. In 2022, after years of operation, the decision was made to end the observatory's flights. The aircraft landed from its final science mission with a mix of pride and sadness among the people who had kept it flying. That ending triggered strong reactions. Supporters argued that shutting down a unique observatory, one that could go where other telescopes could not, and host new instruments with relative ease, was short-sighted. They pointed to ongoing questions in infrared astronomy and planetary science that still benefited from high-altitude access. Critics countered that every big project has a natural lifetime. The field had moved on. New tools in space and on the ground could cover most of the same ground more efficiently. Keeping a flying observatory in the air indefinitely would mean fewer resources for next-generation facilities. There is no simple resolution to that argument. What the story does show is that telescopes are not just about optics and detectors. They are about economics and politics, about which ideas a community of scientists and funders decides to back at any given time. Each large observatory represents years of lobbying, planning, and prioritizing. It is born in committees and reports, as much as in workshops and laboratories. Its death, when it comes, is usually not because of a sudden failure, but because the balance of opportunity and cost shifts. If you imagine yourself on board during one of the final flights, you might feel that mix of wonder and fragility. Outside, at 40,000 feet, the sky is dark and clear, the stars steady points instead of twinkling pinpricks. The telescope door is open, and the mirror stares into wavelengths that human eyes will never directly see. Inside, screens glow with spectra and images scrolling past. People murmur over data, adjust settings, grab quick cups of coffee as the aircraft banks into a new heading to keep a target in view. You know that this is both an everyday routine for the team and a rare, temporary way of seeing the universe. Once you step back onto the runway and watch the aircraft roll toward its hangar, another thought arrives. We have put telescopes on mountaintops and on satellites. We have hung them from balloons and bolted them into aircraft. We clearly are willing to bend almost any machine into an eye if it lets us catch a new kind of light, or a new message from the cosmos. Yet some of the most extreme tricks do not involve wings or sun shields at all. They involve linking antennas spread across continents, or using the bend of gravity around massive objects as a natural lens, or watching how the path of starlight subtly shifts when an unseen planet passes in front of it. These approaches do not look like telescopes in the traditional sense. There's no single big mirror you can point to, yet they let us do something remarkable. They let us draw images of the space around black holes by turning Earth itself into a virtual dish. They let us discover planets that wander alone in the dark, with no host star to betray them, simply by the way their gravity briefly magnifies a background star. They push the idea of what an observatory can be beyond any dome or aircraft. To see how that works, we have to follow light to the very edge of a black hole and watch what happens when gravity itself becomes part of the optics. When you follow light all the way down into the grip of extreme gravity, the geometry of seeing changes. Instead of a beam traveling in straight lines, every ray is bent and twisted by curved space-time. Near a black hole, that bending becomes so strong that light can orbit before escaping. From far away, the region around the hole acts like a strange lens. It distorts images of anything behind it and even lets some photons from the far side wrap around and reach you. To turn that weirdness into a picture, astronomers had to build a telescope with a diameter almost as large as Earth itself. They did not pour a mirror that big, of course. They used an idea we met earlier and stretched it to a planetary scale. Radio telescopes scattered across the globe, from Hawaii to Europe to South America to the South Pole, agreed to observe the same target at almost exactly the same moment. Each one recorded incoming radio waves with precise timing, stamped by atomic clocks. Later, the data from all those antennas would be brought together in central computers and combined. This technique, called very long baseline interferometry, lets the network act like a single dish whose size is set by the maximum separation between antennas. Everything about this project pushed limits. Weather had to be cooperative at many sites at once. Local clocks had to agree to within a fraction of a billionth of a second. The signals being recorded were no stronger than the whisper of a mobile phone on the surface of the moon, buried under noise from the atmosphere and the electronics themselves. Observing sessions generated so much raw data that shipping it over the internet was too slow. Instead, hard drives were physically flown to be fed into correlator machines, which lined up the wave patterns and extracted the faint interference fringes that carry image information. The target they chose for their first big attempt was a giant in another galaxy. At the center of the galaxy, often labeled M87, sits a black hole billions of times more massive than the Sun. It powers a jet of matter that shoots out for thousands of light years, visible across the electromagnetic spectrum. This monster was ideal in two important ways. Its event horizon, the region from which nothing can escape, is big in physical size, and it changes slowly. Gas swirling around it takes days to complete orbits rather than minutes. That means the image does not blur too much while you're trying to take it. When the team finally unveiled what they had reconstructed, the picture was both simple and profound. A bright, uneven ring of radio emission encircling a darker central area. The bright ring came from hot plasma just outside the event horizon, where magnetic fields and rotation energize particles and make them shine in radio waves. The dark patch in the middle was not the black hole itself, but the region where light is either swallowed or bent away from our line of sight. Its size and shape matched the predictions from general relativity for a rotating black hole of that mass at that distance. In one sense, we already believed black holes existed. Decades of indirect evidence pointed that way. But there was something uniquely satisfying about having an image that you could look at and say, "This is the shadow of a black hole cut out of bright gas." More quietly, the measurement also served as another precision test of gravity. If the ring had turned out too big or too small compared with mass estimates from the motion of surrounding stars and gas, theorists would have been forced back to the drawing board. Instead, the picture fit neatly inside the expectations, at least within current uncertainties. After that success, attention turned back toward the supermassive black hole in our own galaxy, the same one whose mass had been weighed by tracking stars with the Very Large Telescope. In principle, that central object subtends a slightly larger angle on the sky than the one in M87 because it is much closer. In practice, it is a trickier subject. The gas around it orbits in minutes instead of days. The structure changes as quickly as you try to take its picture. On top of that, we have to look through more of the Milky Way to see it, which adds scattering and fuzzing from intervening electrons and dust. Still, with improved techniques and more data, the Earth-sized virtual dish eventually drew a picture of that nearer black hole as well. Once again, a bright, lopsided ring and a dim center, though with different details. Seeing both images together gave astronomers a powerful comparison set. Two very different environments, one in a giant elliptical galaxy, one in a spiral like ours, both producing shadows whose sizes are consistent with mass measurements and relativity. Gravity, at least so far, plays fair. It is striking that in these cases gravity is both the barrier and the instrument. The black hole tries to hide itself behind its event horizon. Yet the warping of space-time around it, combined with the patience of observers and the cleverness of very long baseline interferometry, turns that warp into a way to see. The same theme appears when we look at a very different scale of phenomenon, the bending of light by galaxies and clusters. In that arena, gravity becomes a tool for magnifying distant background objects, and for revealing matter that would otherwise be invisible. Imagine a massive galaxy cluster sitting between you and a more distant galaxy. The cluster is full of dark matter as well as stars and gas. Its gravity bends the path of light from the background galaxy, a little in some places, more in others. If the alignment is right, the background object can appear as a stretched arc, a smeared streak, or even as multiple images around the cluster. When the geometry is nearly perfect, you can get a full or partial ring of light, sometimes called an Einstein ring. These distortions are not just pretty oddities. They encode information about the mass distribution in the lensing cluster and about the properties of the background source. By mapping how many and what kind of lensed images we see, astronomers can infer how much dark matter is present and how it is arranged. They can also use the extra magnification to study extremely distant galaxies that would otherwise be too faint to detect. In that sense, clusters of galaxies act as natural telescopes, amplifying the early universe for us. This gravitational lensing does not replace traditional optics. It works only in certain configurations and can be messy, but it gives us a way to see deeper and to weigh the unseen. There is a more subtle form of lensing that works on smaller scales and shorter times. Instead of a huge cluster acting on a background galaxy, you can have a single star, or even a planet, passing in front of a more distant star. As the foreground object moves, its gravity focuses light from the background star very slightly toward Earth. To an observer with a sensitive enough telescope, the distant star appears to brighten for a while and then fade back to normal. The foreground lens may be too faint or too small to see directly. All you notice is the temporary magnification. This is called microlensing. Microlensing is in some ways a frustrating technique because it does not repeat. The alignment that produces the event usually happens once for that particular pair of stars. You see a transient bump in the brightness and then it is over. Yet inside the shape of that bump is a lot of information. The duration tells you something about the mass of the lens and its relative speed. If the lens has a planet, the planet can create a second, smaller blip or anomaly on top of the main brightening. By modeling that pattern, astronomers can infer the presence of the planet, its mass relative to the host, and how far from the host it orbits. This is powerful because microlensing is sensitive to planets that other methods miss. Transit surveys that watch for dips in starlight work best for planets in close, fast orbits that produce many transits. Radial velocity methods, which track the wobble of a star from the pull of planets, also tend to favor tight orbits and relatively massive planets. Microlensing, by contrast, is naturally tuned to planets at or beyond the distance of Earth from the Sun, including those in wide orbits and even ones that may no longer be bound to a star at all. Over the past few decades, ground-based microlensing surveys have reported dozens of exoplanets, including some with orbits far from their stars and some that may be free-floating. Statistical analyses of the events suggest that there could be an enormous population of planets wandering the galaxy without a parent star. Perhaps they were born in disks and later ejected by gravitational interactions. Perhaps some formed directly as isolated clumps in molecular clouds. Either way, if these estimates are even roughly right, our mental picture of the Milky Way has to expand. Between the stars there may be a vast, dark archipelago of lonely worlds, frozen and dim, briefly betrayed only when they drift in front of a background star and make it brighten for a few days. The catch is that the current ground-based surveys see only a tiny fraction of what is out there. They are limited by weather, by daylight, by the density of stars they can monitor, and by the sheer volume of data. They mostly focus on the crowded central bulge of the Milky Way, where many background stars increase the chance of alignments. Even there, they miss events that are too faint or too brief. To truly count these hidden planets and to explore microlensing with the sensitivity it deserves, we need a telescope that can stare at the galactic bulge for long periods with high precision, without clouds, without atmospheric jitter, and in wavelengths that cut through dust. Enter another space telescope with a different mission profile, the Nancy Grace Roman Space Telescope. Planned as a wide-field infrared observatory, is designed with two main goals. One is to study dark energy by measuring how galaxies cluster and how distant supernovae reveal the expansion history of the universe. The other is to conduct a massive microlensing survey toward the center of the Milky Way. Its wide-field instrument will be able to image large swaths of the bulge with resolution similar to older space telescopes, but with a field of view hundreds of times larger. From its vantage point in deep space, Roman will not have to worry about weather or day and night cycles. It will watch millions of stars continuously for weeks, looking for the subtle brightening patterns that signal microlensing. According to forecasts, it should detect thousands of new exoplanets, including many analogs of planets in our own solar system, and hundreds of free-floating worlds that have been cast off into the dark. Because it will observe in infrared, it will also be able to peer through much of the dust that obscures the galactic center in visible light, giving a clearer view of the background stellar population. The vision here is quietly radical. Instead of discovering a few odd planets and marveling at their uniqueness, we move toward building a true census. How many planets does the average star have? How many systems have giant planets far out? How many small, rocky worlds orbit at distances where they could retain liquid water if other conditions are right? How many planets drift free, no longer bound? Each of these numbers feeds back into theories of planet formation and into our sense of how typical or unusual our own system might be. Microlensing also ties into the broader theme you may have noticed. We are learning to use gravity not only as a thing to be measured, but as part of the optical system. Massive objects bend light into arcs that let us map dark matter and magnify the early universe. Black holes warp light into rings that sketch out their shadows. Stars and planets focus background starlight into temporary flares that reveal invisible companions. This is a strange kind of astronomy where the lens and the source are both part of the cosmos, and where your telescope is not just glass and metal, but the structure of space-time itself. We are not stopping at light either. In the last decade, we've begun to detect gravitational waves, tiny ripples in space-time from merging black holes and neutron stars, using interferometers with arms kilometers long on Earth. Those detections have their own kinds of lensing and interference. They give us a new way to listen to cosmic events that does not rely on photons at all. Combined with electromagnetic observations, they create what many people now call multi-messenger astronomy, a way of studying the same event with different carriers of information. Yet there is another messenger that has been quietly carrying messages across the universe all along, through rock, through stars, through planets and people. Ghostly particles that barely interact, that sail through light years of lead as if it were empty space, but that occasionally leave a tiny flash of light in the right kind of detector. If we can learn to read those rare flashes, we gain a way to see into places that light and even gravitational waves cannot easily probe. The next step in expanding our senses does not sit on a mountaintop or ride on a rocket. It sits buried deep in the Antarctic ice, waiting in the dark for the faint signatures of these almost undetectable travelers. From above, you would never know it is there. Snow dunes stretch to the horizon, wind scours the surface, and the only visible signs of human presence are a scattering of buildings and flags. Far below that frozen skin, though, a lattice of cables sinks into the ice, each string carrying dozens of glass spheres that glow to life when something impossible happens nearby. This is the IceCube Neutrino Observatory, a telescope without mirrors that waits not for light reflecting from surfaces, but for the almost undetectable fingerprint of particles passing through the planet itself. Neutrinos are often called ghost particles for good reason. They have no electric charge, almost no mass, and they interact with other matter only through the weak nuclear force and gravity. That means trillions of them from the sun, from distant supernovae, and from cosmic ray collisions in Earth's atmosphere are streaming through your body every second without leaving a trace. To a neutrino, a light year of lead is almost transparent. If you want to catch even a few, you need an absurdly large target and an environment quiet enough that the rare interactions are not drowned in noise. When a high-energy neutrino does finally hit an atom in the ice, it can knock loose a charged particle that shoots off faster than light can travel through that medium. Nothing breaks the ultimate cosmic speed limit, but light moves more slowly in dense materials than in vacuum, so the particle outruns its own light wave. That superluminal sprint produces a shock of blue glow called Cherenkov radiation, a cone of light that spreads out behind the particle like the wake of a boat. The glass spheres buried in the Antarctic ice are digital optical modules, each one containing a photomultiplier tube and electronics, ready to register the faintest of flashes. By timing which modules see light and how bright those signals are, computers can reconstruct the direction the particle came from and how much energy it carried, which in turn tells a story about the neutrino that started the chain. The reason Antarctica is ideal for this is partly geographical and partly geological. The thick ice sheet there is remarkably clear once you go deep enough, with few bubbles and impurities to scatter light. It is dark, cold, and stable, far below the chaotic weather at the surface, and far from human light pollution. You can instrument a cubic kilometer of ice, turning it into a giant three-dimensional camera, without having to dig a cavern or pour a tank. Over time, the ice itself becomes part of the optics, a natural crystal that guides the Cherenkov light into the waiting eyes of the modules. The IceCube array consists of dozens of vertical strings, each lowered through a carefully melted shaft and then frozen into place. Once the water around them refreezes, there is no going back to adjust a cable or swap a sensor, so every component has to survive extreme cold and high pressure for years. On the surface, a modest cluster of buildings houses the computers that collect the data and the people who keep everything running through months of polar night. As neutrino events accumulate, most of what the observatory records comes from mundane sources, like neutrinos produced when cosmic rays slam into the upper atmosphere. Hiding among those daily interactions, however, are the rare high-energy neutrinos that have traveled across cosmic distances from violent astrophysical accelerators. In 2013, the observatory announced the detection of several neutrinos with energies far beyond what typical atmospheric processes could easily explain. These particles carried more energy than the protons smashed together at the Large Hadron Collider, and they had arrived from random directions in the sky rather than from the thin band of the atmosphere above. They were the first clear signs that the universe is peppered with natural particle accelerators that dwarf anything humans can build, flinging protons and nuclei to near light speed and in the process generating neutrinos as byproducts. That realization opened the field of high-energy neutrino astronomy in earnest. A few years later, a single neutrino triggered an even more dramatic chain of events. IceCube registered a high-energy particle coming from a particular patch of sky and sent out an automated alert to observatories around the world. Space-based gamma-ray telescopes, ground-based Cherenkov telescopes, and traditional optical observatories swung to that position and found that a known active galaxy, a blazar with a jet aimed roughly in our direction, was in a flaring state. The combined data pointed to that blazar as the likely source of the neutrino, linking for the first time an individual high-energy neutrino to a specific astrophysical object. It was as if a tiny, nearly massless messenger had carried a direct calling card from the heart of a distant galaxy to detectors buried under the South Pole. This kind of association matters because neutrinos can escape from dense regions that photons struggle to leave. Inside the core of a collapsing star or the crowded base of a jet near a black hole, light can be scattered, absorbed, and re-emitted many times, washing out information about where it came from. Neutrinos, by contrast, pass through most matter almost untouched, carrying a more faithful imprint of the processes that made them. They also travel in straight lines since they are not deflected by magnetic fields the way charged cosmic rays are. By combining what we learn from light, gravitational waves, and neutrinos, we begin to reconstruct a fuller picture of the engines that power the most extreme events in the universe. IceCube is not the only detector of its kind, though it is currently one of the largest. You wait in a huge, quiet volume with very sensitive eyes, and you let the universe come to you. Some detectors are tuned to lower energy neutrinos from the sun and from supernovae in our own galaxy, which carry information about fusion and collapse, while others focus on the highest energies, tracing the most powerful cosmic accelerators. Together they form a loose network of ghost particle observatories that complements the far more familiar map of optical and radio telescopes on Earth and in space. When you look at this network alongside gravitational wave interferometers and traditional telescopes, a pattern emerges that would have been hard to imagine a century ago. Our observatories are no longer just improved versions of the human eye. They are ears for space-time ripples, particle counters buried in ice and water, and radio dishes that stretch from one side of the planet to the other. Each messenger brings a different bias and a different reach. Light tells us about hot surfaces and glowing gas. Gravitational waves tell us about the motions of compact masses, and neutrinos whisper about nuclear reactions and particle collisions deep inside otherwise hidden regions. Step back for a moment and think about how far this is from the way our own senses work. Your eyes catch a thin slice of electromagnetic wavelengths. Your ears respond to tiny pressure waves in air. Your skin feels local heat and touch. None of those senses can perceive a black hole shadow, a ring of distorted radio waves seen by antennas on different continents. None can feel a passing gravitational wave that stretches Earth by a fraction of the width of an atom, or notice a single neutrino lighting up a few photomultiplier tubes 2 kilometers under ice. Yet, by piling up clever instruments designed around specific weaknesses in our perception and specific quirks of physics, we have effectively given ourselves new senses entirely. The story is not finished, of course. Engineers are already sketching ideas for radio arrays on the far side of the moon, where the bulk of the moon itself would shield them from Earth's chatter and let them listen to incredibly long wavelength signals from the early universe. Space agencies plan next-generation gravitational wave observatories that will fly in formation millions of kilometers apart, turning the space between them into arms of a humbly described interferometer that listens for mergers of massive black holes. Concepts for future space telescopes include constellations of mirrors flying in precise formation to act as a single vast interferometer, able to resolve fine details in exoplanet surfaces and maybe even map weather patterns on distant worlds. It is tempting to look at this growing menagerie of instruments and feel that we are closing in on a complete picture. We have eyes that see across the electromagnetic spectrum, ears for space-time vibrations, and detectors for ghost particles. What else could the universe possibly be hiding? But if the history of astronomy teaches anything, it is that every time we open a new window, we find both answers and new puzzles. The first radio telescopes revealed jets and lobes and pulsars that optical astronomers had never suspected. The first X-ray observatories uncovered hot gas halos and accretion disks, and the first deep infrared views changed our understanding of how early galaxies grew. The odd designs we have followed in this journey, from flying telescopes and kilometer-scale ice cubes to segmented mirrors on desert mountaintops and gold-plated sunshields in deep space, are not just engineering curiosities. They are physical embodiments of questions. How do galaxies assemble? How do stars live and die? How common are planets and life? What is the true nature of dark matter and dark energy? And does gravity always behave the way our equations say it should? Each machine slices into that list at a different angle, constrained by budgets and materials and politics, but also by the fact that the universe rarely offers up its secrets in the way that is most convenient for us. The more we ask, the more we discover that full understanding requires stitching together data from many weird, partial views. In the end, the search is as much about us as it is about distant galaxies or exotic particles. Our eyes were never meant to read the afterglow of the Big Bang or the flicker of a star lensed by an invisible planet. Yet here we are, repurposing ice and desert and orbit into extensions of our own curiosity. Every time you see an image of a distant nebula, a black hole shadow, a deep field of infant galaxies, or a plot of a neutrino event, you are looking at the outcome of that stubborn refusal to accept the limits of the senses we were born with. It raises a quiet but unsettling possibility that there are still forms of cosmic information we have not even imagined detectors for yet, entire kinds of messages streaming past us, unnoticed. As we keep building stranger telescopes, You and I are not just watching the universe reveal itself. We are also testing how far our own ingenuity can stretch to meet whatever else might be out there, waiting, just beyond the edge of what we can currently see.